Yo, what's going on guys, Tanmay here for Simple Snippets and welcome back to another video tutorial on data structures and algorithms. And as the title of the video suggests, today we are going to cover a very important topic in data structures, which is the space complexity algorithm analysis. Now if you've been following this entire playlist, this entire DSA course, we've already talked about what is big O notation and what is the time complexity in the algorithm analysis part, but the space complexity is something that we did not cover extensively. So in this video we are going to talk everything in detail about what is space complexity. We are also going to see some examples of algorithms and we are going to calculate the space complexity and understand why it is a little tricky compared to the time complexity. So make sure you watch this video till the end. This is a very important topic, especially from the interviews perspective, from your exams perspective, and just in general also this is a very fundamental topic. And we are going to talk about it more as we move ahead when we see more and more complicated algorithms in this course. So the time and space complexity topics are very important. If you haven't watched those videos, as I mentioned, I'll drop the playlist. Go ahead and watch that and then come back over here. But if you already know what is time complexity and what is big O notation, this is going to be easy to understand. So with that being said, enough of the introduction, let's just jump into it. Now a quick recap, we already know what is algorithm analysis, why is algorithm analysis needed, types of complexity. So just scrolling through the slides, you guys can pause the screen and read the theory. It's pretty understandable. What is algorithm analysis? Is the study and theoretical estimations of the resources of an algorithm, that is the time and space it requires. Then moving on, why do we need algorithm analysis? Because we want to estimate the time and space, right? Because certain times we have some mission critical task wherein the time and space matters a lot. So we've discussed this previously, so I'm just quickly going through the slides. So what does a better algorithm mean in reality? Well, the two major factors are how fast is your algorithm, which is dealing with the time, so that's the time complexity, and how much memory is your algorithm occupying, which is lesser the memory, the better the algorithm, so that's the space complexity, okay? So we are going to focus on space complexity. Then there are other parameters also which are not really that important. The first two are the more important ones. And moving ahead to the real topic, that is space complexity now. The formal definition of space complexity is as follows. Let's cover a little bit of theory before we actually jump into the examples. Now the space complexity of an algorithm or a computer program is the amount of memory space required to solve an instance of the computational problem as a function of the size of the input. Now this sounds like a little tricky and little difficult definition because it's directly from Wikipedia and they don't make it easy, right? So put it in simple words, it is the memory required by an algorithm to execute a program and produce output. That's the very simple definition. So we are dealing with space, which means we are dealing with memory, because every algorithm which we write as a code and run in a computer, it is going to run in your main memory and it is going to occupy some memory. So we want to estimate how much memory is that algorithm gonna occupy. And the reason we want to make estimations is because we already know that when we want to solve a particular problem, generally we have multiple approaches, multiple algorithms to solve the same problem. For example, if you want to search a value in an array, we have two simple algorithms, which is linear search and binary search. So there are two options. Similarly, when you want to perform sorting, we have different sorting algorithms, which means we have different options and each of them have their pros and cons. And that's why we want to make an estimate about algorithms and how much space they are gonna occupy. So this video we are only gonna talk about space and not time. Now similar to time complexity, space complexity is often expressed in asymptotically in the big O notation. So just like we have big O notation for time complexity like big O of n square and so on and so forth. Similarly, space complexity also is denoted by big O notation only, because big O notation is just a mathematical notation which gives us the relation of how the space changes depending upon the input size. So as the input size increases, let's say the size of the array or a data structure is 5. So 5 items are there in a data structure. The space occupied, let's say, is 10 MB. And now if I double the size, is it becoming 20 or is it becoming 40 or is it becoming exponentially growing? That is the, that is what we are actually tracking over here. So this big O notation just gives us the behavior, right? So we have the same big O notation in space complexity also, like O of n log n, O of n square. Now these are all functions which can be shown on a graph mathematically also. We've seen in the time complexity video where n is the input size. Now things get a little tricky, as I mentioned, in space complexity, because there is a little bit of misconception when it comes to calculating space complexity, because there are two ways to look at space complexity. So let's talk about that. Now for any algorithm, a memory is required for the following purposes. Obviously to store the program instructions. So every statement would be actually an instruction. We need to store it somewhere. To store the constant values, to store the variables that we create, And then there are few other things like function calls and jumping statements. Now these function calls are important to keep a track of, because what happens is when you write big algorithms, one function calls other function, the other function might call multiple other functions, and you need to keep a track of who is calling whom, right? So there is a call stack concept, which is basically a stack which is provided by the system. We don't have a track of it, which keeps a track of all these function calls, who is calling whom. We'll talk more about that when we take the example, so stay tuned for that. Don't skip this video, watch this video till the end. So that's where the auxiliary space comes into picture. So what is this auxiliary space? So the auxiliary space is the temporary space excluding the input size, excluding the actual data structure, okay, that we are working on. So let's say you are performing sorting on an array of size 5. So that input size of that array is size 5, right? So excluding that, whatever extra space is required by the algorithm can be considered as auxiliary space, okay? So that's why auxiliary space is the temporary space excluding the input size allocated by algorithm to solve the problem with respect to the input size. Now when it comes to calculating the space complexity as a whole, it includes both auxiliary space and space used by the input. So it's basically auxiliary space plus the space used by the input. Now this is one way to look at space complexity. However, sometimes what happens is we do not consider this as the actual measure. We only look at the auxiliary space. Now if it is getting a little confusing, don't worry, I'm going to solve this doubt and solve this confusion once and for all. Let's actually take an example and let's jump to the digital blackboard. Let's see what happens behind the scenes by taking different algorithm examples. Okay, so as I mentioned, space complexity as a whole is equal to input size plus the extra auxiliary space, right? We just talked about it theoretically. So let's take an algorithm over here, which is basically a very simple algorithm of addition of two numbers. So this is the function. It takes n1, n2. So n1 and n2 are two variables. Let's say they are integer variables. You create a third variable sum, you store the addition in that sum variable and you return that from the function. Okay, very basic. Now if you want to actually estimate the size that this function would take, you can easily try to estimate it by calculating the size these variables will take, right? So let's say n1 is an integer variable, and assuming that an integer variable takes 4 bytes, n1 will take 4 bytes, n2 will take 4 bytes. This sum variable will take, let's say, 4 bytes again. So this is all the memory that all the variables are gonna take. Now apart from that, obviously there will be some overhead, which will be the auxiliary space, which is these instructions, this function call, this return statement. Let's assume that it is gonna take some constant space only, because obviously we are not increasing the number of statements. These statements are gonna be as it is. So let's assume that the auxiliary space, so I'll say AUXSP, is 4 bytes. So if you do a total, the estimated total, now obviously this is the estimated total, this is not the actual total, is going to be 4 plus 4 plus 4 plus 4, which is 16 bytes. Okay, now no matter what is n1 and n2, when I say what is n1 and n2, which is the value, so let's say I am passing 5 and 5, it's going to be sum is going to be 10. So even then it is going to occupy 16 bytes, because that integer variable is going to occupy 4 bytes only in the memory. Let's say if I pass 110 and 90, so the total is going to be 200, but still n1 and n2, that is these two variables, are obviously going to occupy only 4 bytes. Even though I increase the actual value which is stored inside these variables, the memory that they are going to occupy is always going to be constant, right? So no matter what value I pass over here, the total is approximately going to be 16 bytes only, which is actually a constant value. So if you track it on a graph, y being the size in bytes that this program is occupying, and the yellow axis is actually the size, that is the input size. Over here the input size is not changing, the input size is actually going to be a constant value, and we are having two variables, and let's assume that we are just having two variables. So no matter what, we are constantly at 16 bytes only. So the graph would look something like this. So no matter what value you pass, let's say you pass 2 and 2 over here, 2 and 2, it is still going to occupy 16 bytes. If you pass 10 and 10, that is n1 and n2 is 10 and 10, even then it is obviously going to occupy 16 bytes only. So you can see it is a straight line, which means it is a constant space. You can say that it is constant, right? Now the way we represent constant space or constant, constant behavior is by big O of 1. So the final result would be O of 1, because it is a constant. No matter what the input or whatever value you are giving of the input, the size that this program is occupying is more or less going to be 16 bytes only. Hence this algorithm can be considered as a O of 1 space complexity algorithm. So I hope you're understanding this. If you've seen the time complexity videos, this should be easy to understand. Let's take another algorithm to better understand this. Okay, so this time the algorithm is sum of all elements in an array. So we are passing the array, we are passing the size of the array, we are declaring a sum variable, and we are using a loop to iterate through all the elements inside the array. So 0 to n, so n is the size, right? So from 0 till the size, and we are saying sum is equal to sum plus arr of I. So this is that iterator, and then ultimately we are printing it. Now let's analyze this. We have an array which is of variable size of n. So if it is an integer array, let's assume it is an integer array. The size of this array, that is arr, is gonna be equal to n into 4 bytes, right? So if the size of the array is 5, so 5 into 4, 20 bytes of space is gonna be taken into the memory. If it is 10, so 10 into 4, 40 bytes. So n is the variable over here. So n can keep on changing, it is not a constant. Now other things are pretty much gonna be constant because some variable is gonna take 4 bytes. When we initialize the for loop, we are creating an iterator I. So this I variable again is an integer, it's gonna take 4 bytes. And this is for the variables. The other things like initialization of the for loop, the printing statement, the function call, these are all auxiliary spaces. So the auxiliary space, let's assume it takes 4 bytes. Okay. Now if you sum all this up, this time the total, which is actually the space complexity that we are calculating, can be given as n into 4. So that is 4n plus 4 plus 4 plus 4. So these two are the variables and this is the auxiliary space. So we have 12 bytes. So now you can see that we have one variable over here, and this variable will keep on changing depending upon whatever size of the array we pass. So this 12 bytes is obviously constant. So we have ultimately the space complexity as 4n plus c. Now if you remove all the numbers, that is the constant values, we are ultimately left out with O of n. And this is the space complexity for this function, but this is the overall space complexity. We are not looking at just the auxiliary space over here. And if you see the graph of this algorithm, depending upon the size of the array, the graph will also go on increasing. So for n equals to 1, 4 bytes will be allocated for the array, and then obviously plus 12 bytes, right? So 4 plus 12 will be 16 bytes. If n equals to 2, so if I substitute 2 over here, 4 2s are 8, so 8 bytes plus 12 bytes. So 8 plus 12 is 20 bytes, which is somewhere over here. Now if n becomes 3, if I substitute 3 over here, 4 3s are 12, 12 plus 12 is 24 bytes, which is somewhere over here. Now if you see, there is a pattern going on. With every n that is incrementing, 4 bytes are being increased. So the next would be 28 somewhere over here. Then we have 32 and so on and so forth. So if you just plot this line on the graph, it would look something like this. So it would go on increasing in 4 byte sizes. So this is called as linear space complexity. Okay, so I hope you are understanding. But one thing to remember is we are calculating space complexity with this equation or with this formula, which is input size plus auxiliary space. Now as I mentioned, a lot of times what happens is the input size is not considered when calculating space complexity. So if you're wondering why is that, it's because when you are writing an algorithm on a particular data structure, if you consider the size of the data structure, then that space complexity will always be there. You want to calculate the space complexity of the algorithm and not the input that you're providing to the algorithm, because you want to track how much space is taken given a particular input size. So if you calculate the space of the input size also along with it, that basically rules out the purpose of actually doing or calculating the space complexity itself. Now if it is not still making sense, let's actually take 2 more examples. So far so good. I hope you understood what is space complexity and how you calculate space complexity using this formula, which is input size plus auxiliary space. Now there is another way, as I mentioned, wherein we are only considering auxiliary space. And why is that so? We'll see that in this further 2 examples. Now generally when we look at algorithms, we can broadly classify them into iterative or recursive. Now iterative is when we are using a loop to perform multiple activities over and over again, and recursive is when we are using the function to call itself, which is basically the concept of recursion. Now we've already talked about recursion in the previous tutorial when we did the merge sort in this series. I have a separate dedicated video also which explains what exactly is recursion and how it works behind the scenes. So I'll drop those links. If you have even 1% confusion about recursion, please watch that video. That is very, very important and very, very easy and detailed to understand, and then come back over here. But as I mentioned, generally we can broadly classify them into two types, that is iterative and recursive. Now if you see algorithm 3 and algorithm 4, both are solving the same problem. That is, the problem statement is same. That is, we want to calculate factorial of a number, but here we are using the iterative method. Algorithm 4 again says factorial of a number, but we are using the recursive method. Now let's actually calculate the space complexity over here using this formula, and then we'll also only calculate the auxiliary space complexity also. Okay. So here we are declaring a variable int fact, then we are using the loop. We are going from I to n. So the n is basically the number that we want to calculate the factorial of. Okay. So n would be something that is going to be coming from the user. So let's say n equals to phi. So if I say phi, the factorial of phi is going to be phi into 4 into 3 into 2 into 1. So I hope you know what is factorial and how to calculate that mathematically. When I say n equals to phi, this is what should happen in the algorithm. So let's say I am saying n equals to phi over here. Okay. So I'm declaring a variable fact. I'm going from int I equals to 1, I less than equal to n. So n is phi. So I'm going to go till phi and then I plus plus or plus plus I. I'm going to say fact is equal to fact star I. Now this is how factorial is calculated. I have a program also on this separately. If you don't know the logic, just actually type this code in your program and see how it goes step by step. You can try run it, and ultimately you will get the factorial and you can return it from this function. Okay, and it will run for 5 times. So here if we actually do the space complexity, we have a fact variable fact which is going to take 4 bytes, assuming that is the integer variable. We have n is also going to take 4 bytes no matter what we pass, right? Because it is a variable, it is not an array which is having a variable size. It is just a variable which is taking one integer value. So no matter what the integer, be it 5 or 5000 or 10,000 or whatever, it is always going to take 4 bytes. Then we have the iterator I inside the for loop, which is going to take 4 bytes. Now depending upon what you pass over here, 5, this for loop is going to run for 5 times. If you pass 6, it is going to run for 6 times. So the time complexity over here will variate, but the size will remain the same because we are not creating additional variables in the loop. We are using the same variables. And since we are only interested in the space complexity, the space will always remain the same. No matter how many times this loop is going to run, the space is always going to be the same because we are not creating more variables in every iteration. We are using the same variable in every iteration. So space obviously going to be the same. And then ultimately, let's say the auxiliary space, which is used for creating these program statements, running this program statements and storing it somewhere, initializing the for loop, using this return statement. All these instructions will also be stored, right? So the auxiliary space, let's say, is 4 bytes. Now in total, if we actually go ahead and use this space complexity formula, I'm going to say S over here is going to be equal to these 4 plus 4 plus 4, 12 bytes plus the auxiliary space, which is again 4 bytes. So this becomes a constant number, 16 bytes, right? So this becomes a 16 byte constant number. So the space complexity over here can be given by big O of 1. So whenever we get a constant number and not a variable, we denote it as big O of 1. So no matter what the size, the 16 byte is going to be constant, and the graph is pretty much going to look something like this. So this is constant space complexity. Now coming to this recursive algorithm, let's see what happens at recursive algorithm. Now the algorithm is as follows. Let's say n is again equal to phi, and we are passing this in this function. So this is entirely inside a function. Okay. So first thing we check if n is less than equal to 1. If it is less than or equal to 1, we have to return 1. Else we are giving a recursive call and we are saying return n star factorial, which is actually the name of this function, factorial 2 of n minus 1. So we are recursively calling this same function. So factorial 2 is actually the name of this function. I have not written it over here, but basically if I would have to show it, it would look something like this. Let me just do it. In fact, let me just put it over here. Okay, so as you can see, I have modified this and I've added the function name over here. So we are calling the same function, but this time we are saying n minus 1. So what will happen? For the first time we pass phi, right? N is equal to phi. phi is not less than or it is not equal to 1. So we'll go in the else part. And now we are giving a call to the same function factorial 2 of n minus 1, which is phi minus 1. So basically what is happening, first function we are passing phi. Now inside this we are saying phi into this again function is called, but this time it is f of n minus 1, which is 4. So we still don't know what is f of 4. We have to call f of 4 and f of phi will be paused. So there is a call stack which is going to be generated by the system itself, and f of n will actually call f of 4. So f of 4 will be placed in the call stack. We're going to say phi into f of 4, right? Now we don't know what is f of 4. We are just passing 4 over here, and now another function call will be given to the same function. It will become 4. So the first function has called this recursively, and now we are passing 4. Is 4 less than or equal to 1? No. So again we'll go in the else part, and now this time it would be n into again calling the same function. So this time n is 4. So now it would be 4 into f of 4 minus 1. So it is f of 3. So now the call stack will maintain this because we still have to calculate what is f of 3. So we have 4 into f of 3. So f of 4 has basically called f of 3. And similarly we will have more calls. So it would be 3 into f of 2. F of 2 will call f of 1. So that would be 2 into f of 1. And when n is going to be equal to 1, that's where this condition will become true. If n is less than or equal to 1, it is equal to 1. So we're going to return 1. So we will not go further from this, and no more entry will be added to the call stack. So this call stack is nothing but a memory space, okay? So this is a system provided memory space which is keeping a track of which function is calling which function, right? And since this is a recursive call, multiple function calls are made. So this is basically a memory space. So this might be maybe let's say 1 byte. We're just assuming this can be 1 byte. This can be 1 byte. It would be a standard size, but as the number of function calls increase, the number of bytes will also increase. That's what I'm trying to say. So when it becomes f of 1, we are returning 1. So 1 will be returned over here. So 2 into 1 will be returned, and this would go back to the calling function. So f2 had called f1. So 2 into 1 is 2. So instead of f2, now we have 2 over here. So I'm going to erase this, and we are getting back 2 over here. So 3 into 2 is 6. So 6 will be returned back over here, which was called by f3. So f3 now becomes 6. So 4 into 6 becomes 24, right? So that would be returned from over here to f4. f4 had called f3. We got the result of f3 as 6 into 4, 24. So 24 will be substituted in the place of f4. Now 24 into 5 is going to give you 120. And that 120 will be ultimately given over here, returned over here. And we are going to get the result as 120. Now what just happened over here is I explained to you what is happening behind the scenes in short in a quick way when the algorithm is a recursive type of algorithm. And as you can see, as the number of recursive call increases, the call stack memory also keeps on increasing. So this is where keeping a track of the space for recursive functions become a little tricky, because those individual intermediate function calls will also have some memory allocations. For example, in one function call, what is happening? We are passing n. So n is gonna take 4 bytes because n is an integer variable. And then for one function call, we have if statement, we have else statement. So we have auxiliary space for one function call. So the auxiliary space, let's assume, is 4 bytes. But remember that we are calling this same function for 5 times. So 4 plus 4 for one function call, which is equal to 8 bytes. And this same function is called 5 times. So 8 into 5, which becomes 40 bytes, right? You can see there is an exponential growth over here. So when you calculate the space complexity for a recursive function, it would be more dependent upon the auxiliary space, that is this part, and not the actual input size. This input size is gonna be the constant over here, because whatever number you enter, that is okay. But the number of recursive calls depend on this n. And hence this time, the input size is gonna be like 4 bytes only, because that's the size of the integer variable that is going to be stored. But the auxiliary space now becomes variable. The auxiliary space is increasing, which is directly proportional to the number that we are passing. So if you are passing 5, we are getting 5 recursive calls. If you are passing 6, we are gonna get 6 recursive calls. And then this is gonna be n into the bytes for one function call. Bytes required for one function call. So you can see that this can be said as a linear space complexity. But here we are not more interested in the input size. When it comes to recursion and recursive functions, we are more interested in the extra space that is required to maintain this call stack and to call the recursive functions and keep a track of them. And that's why here we are gonna give this space complexity of O of n, but this O of n is more important or only relevant because of this auxiliary space calculation and not because of the input size. So that's why sometimes only auxiliary space is important, especially when we are giving recursive calls. And if you just Google it out, if you just Google the space complexity of a sorting algorithm, or let's say space complexity of a searching algorithm, for example linear search, you'll get the result as O of 1. Now technically for a search algorithm, for a linear search algorithm, let's say you have, let me just erase this out. So let's say you have an array of size 5 and you have some integer variables and you want to do a linear search and you want to search for this number 0. So you'll start from 1, 2, 8, 2 and then you'll reach to this, right? So basically you'll need 5 iterations, but the size of this input array is always going to be same no matter how many iterations you take. So the space complexity over here is going to be 5 only. There is no auxiliary space required, right? So if you calculate the space complexity for a linear search, it is going to be the constant size of the input array, which is going to be n bytes, plus the auxiliary space, which is going to be a constant number, because it is not going to change. The algorithm instructions are not going to create more memory allocations. But this n byte is not considered as O of n. If you just Google it out, the space complexity of a linear search is always going to be O of 1. And that is because here the input size is not considered. We want to just calculate whether this algorithm is taking extra auxiliary space or not. And hence we have multiple results. Sometimes you get O of n as the result if you Google, and sometimes you'll get O of 1. And it is because there are two ways at looking at space complexity, and I hope now it is clear that what is space complexity, what is input size, and what is auxiliary space, and how auxiliary space is important and when it is important. So yeah, this was the entire concept of space complexity and how we can calculate space complexity and why it is important, and the two different ways in which space complexity can be calculated and when is auxiliary space important and when it is not. So yeah, that's it for this video guys. I hope this concept of space complexity is clear to you now. If you like this video, if you've watched this so far, please give this video a like. Let me know in the comments how this video was. Do share it with your friends, and I'll see you guys in the next video. Peace.